All right, well, so today we are going to be talking about operational amplifiers, or more commonly called the op amp. So as I mentioned way back at the beginning of this class, literally on the first day that we had, an operational amplifier is an example of a circuit element that contains more than two terminals. So I'm about to switch over to a different screen, and I'm going to show you what a simplified version of the internal workings of an op amp look like. So this is the functional block diagram of a TI mu-A 741 op amp. This is a general purpose operational amplifier that is used in a lot of circuits, ranging from simple electronics, like what you might find in a guitar effects pedal, up to things like televisions, radios, and all that kind of good stuff. This particular simplified version of the circuit contains 22 transistors, 11 resistors, 1 diode, and 1 capacitor. Now, we are not going to analyze this circuit because at this point in our circuit analysis career, we literally don't know what the overwhelming majority of these things are, okay? Luckily for us, most operational amplifiers, at least in what I'm going to call a negative feedback configuration, which we'll talk about what that means in a little bit, can be analyzed using just a couple of simple rules that explain how they behave, and then by applying regular circuit analysis techniques. One thing that I do want to point out here is we can see that there are actually 7 terminals for this device, okay? One labeled in minus, one labeled in plus, one labeled offset N1, offset N2, VCC plus, VCC minus, and out. So with that in mind, let's look at what our representation of an op amp is going to look like. So our op amp, we are going to represent with this triangle shape. The triangle shape is the general schematic diagram for an amplifier block. And we are going to have 2 terminals on the left-hand side. One of them will have a plus sign associated with it, and one of them will have a minus sign associated with it. The plus sign terminal is the non-inverting input terminal. The one with the minus sign associated with it is the inverting input terminal. On the right-hand side, we are going to have our output terminal. And for the overwhelming majority of our circuit analysis, these are the 3 terminals that we are going to deal with. I am about to include a couple more. So I'll do these in blue. So this will be the VCC plus terminal, and down here will be the VCC minus terminal. So these terminals are used to connect external power to our amplifier. So an op amp is an example of what I'm going to call an active circuit, where an active circuit means it requires external power in order to function properly, right? So resistors, capacitors, and inductors are passive circuit elements because they exhibit resistance, capacitance, and inductance regardless of whether or not they are connected to anything. An op amp can only amplify signals if power is provided to the amplifier circuit itself, okay? So this VCC plus terminal and this VCC minus terminal aren't going to show up in any of our analysis, but they do have to be included anytime we try to practically realize an op-amp circuit, which is what we're going to be doing in the lab on Wednesday. Okay. We're also going to have another set of optional terminals. I'll put these in green. So this is going to be offset plus, and this is going to be offset minus. Not all op amps have these offset terminals, but most single op amp chips do. So effectively, these offset terminals are there because the manufacturing process for op amps isn't a perfect thing. And so what can happen is that even with like if you power up your op amp, so you apply voltage at VCC plus and VCC minus, if you were to short out your input pins, meaning that there was no voltage at the input whatsoever, you might see some small voltage at the output. So your offset pins are used to cancel out that small voltage at the output so that when you have zero input, you have zero output. So it's literally just to correct for manufacturing errors. They're not going to show up at all in any of our analysis. We're going to assume ideal op-amp behavior, and we're going to effectively assume ideal op-amp behavior in our practical circuit that we do in the lab as well. So I just want to make you aware that these terminals exist and what they're used for, but largely, unless you're dealing with high precision systems, you likely don't need to worry about them at all. And as I said earlier, not all op amps even include them. Excuse me. So this is our op amp and its terminals. Now I want to talk about the concept very briefly of positive and negative feedback. Okay. So let's say that I have an op amp circuit like so. And I connect some input voltage source here. Let me throw another resistor in here just for the sake of argument. Like so. So this resistor up top is what I'm going to call my feedback resistance, because it feeds back some portion of the signal at the output to one of the input pins. This is an example of positive feedback. Because it provides feedback between the output pin and the non-inverting input pin. Positive feedback is used to make oscillator circuits. Okay. So effectively, positive feedback largely makes systems unstable, but that instability can be useful when you're trying to get oscillations and things like that. In contrast, down here, I'm going to draw a negative feedback op-amp circuit. It's going to look practically identical, except that the feedback resistance is going to be placed between the inverting input terminal and the output terminal. So negative feedback is used to increase system stability. What we are going to see is that in a negative feedback system, our voltage gain, or the ratio of the output voltage to the input voltage, is largely going to be dependent on the resistors that we connect to our op-amp circuit. Beyond the scope of this class, negative feedback also provides bandwidth extension, lowers noise, and has many other positive effects, all of which are counteracted by a reduction in the overall system gain. All of the circuits that we are going to deal with here in circuits 1 are going to be negative feedback circuits, meaning they're always going to have a resistance connected between they're always going to have a component, let me say that, connected between the inverting input terminal and the output terminal. So in a negative feedback configuration, like the one I've drawn here, we can actually come up with two rules that govern our op-amp behavior. Okay. So the first rule is that no current can flow into or out of the input terminals. I'm going to underline input here because that's very important. So what I mean by that specifically is, let's call this current right here I superscript minus. Okay. This current must be 0 amps if we have a negative feedback amplifier. And similarly, this current right here, if my stylus will allow me to write, which I'm going to call I plus, must also be 0 amps. So no current can flow into or out of the input terminals. So the reason for this is that the input resistance of an operational amplifier is very large. Okay. So for this 741 amplifier right here, if we were to scroll up, let me see if I can find it. Our input resistance, let me highlight it right here. Let's see, pen. Input resistance right here is at a minimum 0.3 mega ohms, but is typically 2 mega ohms. Okay, so that's a resistance of 2 million ohms if we were to look in to the input terminals of our op-amp. So this particular op-amp circuit uses a bipolar junction transistor technology node. Okay, so it has a internal resistance of around 2 mega ohms because of the way that it's designed. Some op-amps use MOSFET, or metal oxide semiconductor field effect transistors in their circuitry. And typically speaking, the input resistance of a MOSFET-based op-amp is on the order of tera ohms, or 10 to the 12 ohms. Okay, so for the most part, there will be some small amount of current that is flowing into the op-amp terminals, but it will typically be on the order of nanoamps to picoamperes or smaller. And so we consider that effectively or essentially to be 0. So our first op-amp rule, no current can flow into or out of the input terminals of our op-amp, is because of the large input resistance of the op-amp itself. Our second rule is there can be no potential difference between the input terminals. So what that means is we are guaranteed a voltage drop of 0 volts between our input terminals. Another way to think about this is that if the voltage at one of our terminals is known, so for instance, our non-inverting input terminal voltage V plus here is connected directly to ground, that means our voltage here at our inverting input terminal must also be 0 volts because there is no potential difference between our input terminals. So a shorthand notation that I like to use for this rule is simply to say that V plus, the voltage present at our non-inverting input terminal, must be exactly equal to V minus. Now, this rule is a result of really two things. One, that our open loop gain of our op amp is usually on the order of a few 100,000 to a few million. And the second part of it is that we are also in a negative feedback configuration. Me explaining this or deriving it further would be beyond the scope of this class, but it is one of the things that we get into early on in circuits 2 when we get into much greater detail about the behavior of op amp circuits. So for those of you that are interested and also happen to be electrical engineers, you'll hear me talk about it in great length next quarter. All right, so what we're going to do now is we are going to analyze circuits using these two rules and our conventional circuit analysis techniques, and we are going to develop a simple algorithm, because I like to have simple multi-step processes for effectively analyzing any op amp circuit that we could be interested in. So what I would like to do actually is work you guys's web work assignment with you to cover this material. So if you give me just a moment, I'm going to pop onto web work and we're going to look up things here. Draw it and just make up some numbers. So let's call this homework 16.1. So we have our op amp circuit like so. Our non-inverting input terminal is connected to ground. We have some feedback resistance connected between our inverting input terminal and our output terminal. So let's make this easy and call this a 5 kilo ohm resistor. Here is the output voltage that we are trying to measure. And if I'm not mistaken, over here on the left, we have a current source. And let's make this a 1.5 milliamp current source having this particular direction. So our first step is going to be apply rule number 1 and determine the voltage present at our non-inverting input terminal. So rule number 1 says that this current has to be 0 amps and this current has to be 0 amps. And now we are to find our voltage at this node. So who can tell me what that voltage is? 0, absolutely. It's connected directly to ground. And I'll write this over here. V plus is equal to 0 volts. Our second step is going to be apply rule number 2 and write a KCL equation at the inverting input node. So applying op-amp rule number 2 tells us that our voltage at our inverting input terminal, V minus, must also be 0 volts. And so what I'm going to do now, I'm going to do it in pink, is I'm going to write a KCL equation. So I'm going to add this current, which is leaving my inverting input terminal, plus this current is equal to 0, because I know that no current can branch off and flow to the right. Now, before I write this expression, I need you guys to understand that we are dealing, whenever we're dealing with op amps, we are using nodal voltages, okay? So our voltage at our non-inverting input terminal is measured with respect to ground, our voltage at our inverting input terminal is measured with respect to ground, and our voltage measured at the output terminal is measured with respect to ground. So another way to think of our output voltage would be like this, okay? So I'm pointing this out because we are going to be writing effectively a nodal analysis equation here at our inverting input node. So in this case, we are going to have negative 1.5 milliamps plus, so that's the current flowing to the left out of our inverting input terminal. Now we're figuring out what the current flowing up out of our inverting input terminal is. So we're going to have V minus, which we know to be 0, minus V out divided by 5 kiloohms is equal to 0. And our third step simply going to be solve our KCL equation for V out. So it should be pretty obvious here that I'm going to have 0 minus V out over 5 kiloohms is equal to positive 1.5 milliamps. So negative V out is going to be 1.5 milliamps times 5 kiloohms. And from here, we could say that V out is negative 7.5 volts. So this is our basic 3-step process, okay? Now, in very special instances, we are going to have to modify it. There are at least one problem in this homework set where we have to modify this process, but for the overwhelming majority of the time, it's just these 3 steps. when we get to one of the problems that we'll have to modify our process, I will identify it. I will talk to you all about why we have to modify it and why it really doesn't make any sense, but we'll get to that in a minute. Okay. So any questions about this particular circuit? Yes, all of the grounds are the exact same ground plane and node. Absolutely. So they are all at the same potential of 0 volts. All right. So before we move along to our second homework problem, I want to show you guys a couple of kind of red herring type things that you might see in problems that you're asked to work. I call them red herrings because from an analysis perspective, they don't really do anything. That being said, from a circuit performance perspective, they can be pretty important. Okay. So the first thing that you might see is some resistance here, which I'm going to call R plus. Okay. Now, the practical reason for this resistance existing is to limit what's called the input bias current of the op amp. So this goes into effectively having output signals when your input signal is 0 kind of thing. From an analysis perspective, this resistor serves no purpose whatsoever, because since no current can flow into the non-inverting input terminal, that means no current can flow through that resistor I've labeled as R plus. So there's no current flowing through it and there's no voltage drop over it. So it may as well not even be there. Okay. So practically speaking, there's absolutely a reason to put it there. From an analysis perspective, it doesn't really do anything. So if you see a resistor directly between your non-inverting input terminal and ground, since no current flows through it, no voltage drop occurs across it, and we can effectively ignore it. Another thing you might see is a load resistance, RL, connected between our output terminal and ground. Excuse me. So op amps are very regularly used to drive circuits or drive some load. That being said, in a negative feedback configuration, when we're dealing with an ideal op amp, the load resistance doesn't actually do anything. Okay. Meaning that our circuit analysis would not change at all, even if that resistor RL were there. Okay. The only resistor value that would change our analysis would be if RL were 0 or a direct short circuit to ground, which would obviously force V out to be 0 because it would be connected to ground with a wire. Okay. So these are two resistors that you might see in circuits that you're asked to analyze. And regardless of whether or not they are there, our three-step analysis rule or three-step analysis procedure would give us this exact same result. All right, now let's look at homework 16, problem 2. So we have a nearly identical circuit, except that there is a voltage source connected to our non-inverting input terminal. Let's see what's going on in chat. Excuse me. All right. Well, let me. I'll explain that while we look at this one, Hannah. So I'm going to draw roughly the same circuit. Minus, plus, For the sake of argument, let's call this 3 volts. Let's make this 4 kilo ohms. Here is our output voltage. Let's make this 2 milliamps. So Hannah asked the question, how do we know which voltage is V plus and which voltage is V minus? Okay, so I'm going to write this out here. V plus is the nodal voltage at the non-inverting input terminal. And V minus is always the nodal voltage at the inverting input terminal. So always, the voltage that's connected to this plus sign is V plus. And always, the voltage that's connected to the terminal at this minus sign is V minus. Does that clarify things, Hannah? All right. So let's apply our 3-step process to this particular problem. So step number 1, once again, apply rule 1 and determine V plus. So rule 1 says this current is 0 amps and this current is 0 amps. What is our voltage at our non-inverting input terminal? 3 volts, absolutely right. Rule number 2, or excuse me, step number 2 is to apply rule 2 and write KCL equation at our inverting input node. So what is the voltage here at V minus? Also 3, absolutely. All right. Now we're going to write our KCL equation. So I'm going to add this current plus this current together with the understanding that no current can branch off and flow to the right. So that's going to look like -2 milliamps plus 3 volts minus V out over 4 kilo ohms is equal to 0. And now we have step number 3. Solve our KCL equation for V out. So doing some mental math here, we're going to have 3 minus V out is equal to 8 volts. Subtract 3 from both sides gives us negative V out is equal to 5 volts. So V out must be negative 5 volts. You want to throw that into a numerical solver and verify that I did the math correctly. by all means do so. So any question about this circuit? All right, so let me ask you guys a slightly different question. How bad does this analysis seem? Anything seem troublesome or difficult about what we're doing here? Not too bad until it gets bad. So I would argue that, in my opinion, and again, I'm saying this as a jackass with a PhD, it never gets bad, at least with negative feedback circuits. In fact, after we work this homework set, I'll work one of the quote unquote hardest op-amp style problems that I could give you from one of our old tests. And we'll see that this 3-step process is literally all you need to do to analyze it. All right, so let's look at our next homework problem. Excuse me. So if memory serves me correctly, this is where we are going to have to modify our analysis. Yep. So we have a voltage source connected to our non-inverting input terminal, but we also have a voltage source in our feedback loop. All right. So let me draw this out. Let's make this 4 volts. Let's make this 2 volts. 1 kilo ohm. And we're going to figure out what V out is. So our first step is going to be the same. Apply rule number 1 and determine V plus. So what is V plus? Two volts. No, that's incorrect. 4 volts. All right. Our second step is to apply rule number 2. And here, instead of applying Kirchhoff's current law, we're going to apply Kirchhoff's voltage law. So I'm going to do a couple of things here just to modify stuff so that it's obvious what's happening. So the 4 volt source that I've applied on the left connected to the inverting input terminal isn't actually there, okay? But we know that our voltage present at our inverting input terminal must be 4 volts because we have a negative feedback amplifier and we're applying our ideal op-amp rules. Okay. So I drew it there to make it obvious when I write my Kirchhoff's voltage law loop. I'm going to start at this ground here. And end at this ground here. So if I start at ground and I end at ground, I have completed a path over which I can write a KVL expression. So I'm going to have negative 4 volts plus 2 volts plus the voltage drop over my 1 kilo ohm resistor plus V out is equal to 0. Okay. So right now it looks like I have two excuse me, 2 unknown quantities, right? I would argue though, let me draw this in red since I didn't write it down and I should have. We know that these 2 currents are 0. What's the current flowing through the 1 kilo ohm resistor? Anybody have any thoughts on what that might be? So I see 0 from Levi and -2 milliamps from John. So Levi is actually correct, right? So the reason why I say that, if there's no amps flowing here, this must also be 0 amps, right? Which in turn means this is 0 amps. The 4 volt source that I have directed out to the left, like I said, isn't actually there, right? So if any current flows through the 1 kilo ohm resistor, that means current has to be flowing into or out of our inverting input terminal. So the voltage drop across our 1 kilo ohm resistor must be 0 volts. From this, we can now simply solve our KVL equation for V out. And so that's going to look like V out is going to be 4 volts minus 2 volts is equal to 2 volts. Okay. So this is how we would do it by modifying things, modifying our procedure. So our second step changed from apply rule number 2 and then write a KCL equation to apply rule number 2 and write a KVL equation. Another way to think about this, we could just write a KCL equation at the supernode that contains our inverting input terminal, would also get us the exact same results, but you guys kind of don't do well with supernodes, so I'm trying to avoid that. So let me say something else here really quickly. Okay. There is no practical reason why you would ever actually put a voltage source in your feedback loop like this. Okay. So problems like this are literally just constructs to test you guys' knowledge of the application of the ideal op-amp rules. You would, I have never once seen any circuit where you actually use a voltage source in your feedback loop. I've seen wires, I've seen capacitors, I've seen inductors, resistors, switched capacitors, all kinds of good stuff like that, combinations of elements, but never once have I seen anybody put a voltage source in their feedback loop for any real purpose. Okay. So 99.9% of the time, you're going to do the 3-step process that we did on the last 2 problems. If and only if you have a voltage source in your feedback loop, will you need to write a KVL equation instead. And arguably, you could still just apply KCL. Let me put it in purple. If you did KCL here and also KCL here, and then solve that two equation system, you get the exact same result. So, excuse me. All right. Let's look at our fourth homework problem. So I like this one. You guys generally don't care for it. So we have our op-amp circuit. I want you guys to notice here that the terminals on the op-amp have been flipped from all of our previous examples. So if we look at the previous problems, our inverting input terminal was on top in all of our instances. In problem number 4, our inverting input terminal is on bottom. That does not in any way, shape, or form change how the circuit is going to behave. Okay, so I just want to be clear about that. It's just drawn slightly differently. So our non-inverting input was connected to ground. Then we had some feedback resistance. Let's call it 8 kilo ohms connected between our inverting input terminal and our output terminal. Connected to our output terminal is a current source. Let's call this 1 milliamp. And we're trying to find the voltage present at our output terminal, Vout. So because we don't have a voltage source in our feedback loop, we're going to go back to the normal 3-step process. So step number 1, apply rule number 1 and find V plus. That 0 amps, that 0 amps. V plus is equal to what? 0. Absolutely right. Now we have rule number 2. Excuse me, step number 2. Apply rule number 2 and write KCL equation. At our inverting input terminal. So rule number 2 tells us that this voltage is also 0 volts. And our KCL equation is effectively just going to be 0, meaning the current flowing through our 8 kilo ohm resistor must also be 0 amps. So step 3, solve for Vout. What does Vout have to be? I disagree. Zero. Absolutely right, Justin. So let me try to explain why this is 0 in a slightly different way. Okay. So if I start here, I go across this gap, I go across my 8 ohm resistor, and then here, going from ground to ground, I have -0 volts plus -0 volts plus V out is equal to 0, which means simply that V out is equal to 0. So one question for students that struggle to understand this, what they commonly ask is, well, where the heck does that 1 milliamps of current go? So our ideal op-amp rule number 1 states that no current can flow into or out of the input terminals. So what that means is that 1 milliamp can absolutely flow into the output terminal on its path towards ground through our power supply voltages and all that kind of good stuff. Okay, so this one is intentionally tricky. Okay, I can understand why many of you intuitively think the answer should be 1 milliamp times 8 kilo ohms should give you 8 volts. But you have to understand that no current can be flowing through that 8 kilo ohm resistor, because to do so would involve current flowing into our inverting input terminal. Okay, so our ideal op-amp rules must be satisfied first. This problem is almost exactly the same thing as problem number 3. Except that there's not a resistor in the feedback loop as well, but we learned that the resistor didn't actually do anything. So I'll leave one for this one for you guys to do. Let's look at number 6. So this is the one that's actually closest to the circuits that you would actually be expected to analyze. Like this circuit has a purpose. This is an actual amplifier circuit. It is also extraordinarily similar to in-class assignment problem number 1, just as a heads up. So homework number 16, problem 6. Make sure I get this drawn correctly. All right, so our non-inverting input is grounded. I'm just making sure I'm drawing that right. Let's call this 4 volts, 8 kilo ohm, 2 kilo ohm, call this 12 kilo ohm. Was there a load resistor as well? Yeah. $10 kilo ohm. And here is V out. So this circuit looks considerably more difficult than the other ones, but in truth, it is just as simple. Okay. So just using that same boring 3-step process that I am trying to burn into you guys' brains, we have the application of step number 1. So we apply rule number 1 and find V plus. So rule number 1 states that this current is 0 amps. And this current is 0 amps. And now we find this voltage. And it is going to be what? 0. Absolutely right. Now we move on to step number 2. Apply rule number 2 and write KCL equation at the inverting input node. So that means we recognize that this voltage here is 0 volts. And now we are going to write our KCL equation. So we're going to be adding this current to the left, plus this current down, plus this current up and to the right, and setting them equal to 0. So our current to the left is going to be 0 volts minus 4 volts over 8 kiloohms. Our current down is going to be 0 volts minus 0 volts over 2 kiloohms. So this resistor right here was just there to trip you up. And then we're going to have 0 volts minus V out over 12 kiloohms is equal to 0. And our last step is simply to solve our KCL equation for V out. And with a trivial amount of algebra, we are going to find that V out is equal to, let's see, 4 times negative 12 over 8. So that's 4 times 3 over 2, negative 6 volts. And if you want to verify that, by all means, throw our full KCL equation into your numerical solver. So I would argue that this type of circuit is actually more in line with what you're expected to be able to analyze. The other problems in this homework set are more so about the correct application of the ideal op-amp rules. This one actually involves analysis. So let's take this to the extreme. I'm going to come up with a problem right now that is similar to the hardest problem I've ever put on one of your exams, with regards to op-amps anyway. So let's say that this is our circuit. right? So this is a circuit that we are going to analyze. It looks far more difficult than anything we have seen today. There are three different sources. Some of them are connected to the inverting input terminal. Some of them are connected to the non-inverting input terminal. This is a hot mess of a circuit. And literally, all we need to do to analyze it is apply that same simple three-step process that we've been doing. So, step number one, apply rule one and find V plus. Okay. So rule one says that this current is 0 amps. And this current is 0 amps. So what's this voltage V plus going to be? So I disagree, Justin. Let me explain my reasoning as to why I disagree. Our current of 1 milliamps is leaving our source. It flows through the 2 kilo ohm resistor, and then all of that same 1 milliamps of current must flow down through the 4 kilo ohm resistor. Our voltage V plus is a voltage measured with respect to ground. So it's the same thing as the voltage drop across the 4 kilo ohm resistor. So from that, I would argue that V plus must be 4 volts. Okay. So to make this very clear, our voltage V plus is a nodal voltage, meaning that is measured with respect to ground. So it is the same thing as the voltage drop across the 4 kilo ohm resistor in this case. Since 1 milliamps of current flows through the 4 kilo ohm resistor, the voltage is simply 4 volts. Anybody have any questions, comments, or concerns about that step? All right. So, well, let me see what the chat says. I'm not ignoring the 2 kilo ohm resistor. The 1 milliamps of current does flow through that 2 kilo ohm resistor, so there is a 2 volt drop over it. That being said, the voltage drop over the 2 kilo ohm resistor is not the voltage present at our non-inverting input terminal, because our non-inverting input terminal voltage is measured with respect to ground, right? So another way to think about this, so John is suggesting that there's a 2 volt drop over the 2 kilo ohm resistor, which is absolutely true, but there's also a voltage drop across this current source. That 2 volt drop plus the voltage drop over the current source would also be our nodal voltage with respect to ground. I would argue that the current source must have a 2 volt drop over it with the polarity that I have indicated. Excuse me, that the 1 milliamp current source has to have a 2 volt drop, because 2 volts plus 2 volts will equal to 4 volts. So if we wrote the Kirchhoff's voltage law equation, yep, absolutely. All right. So are we ready to apply step number 2? So for step number 2, we apply rule 2 and find, excuse me, not and find V minus, because V minus is effectively given to us, and write a KCL equation at the inverting input node. So applying rule number 2, we know that this voltage V minus must also be 4 volts. And so now we're simply going to add this current plus this current plus this current plus this current together, right? So that's going to look like 4 volts over 6 kiloohms minus 2 milliamps plus 4 volts minus 7 volts over 5 kiloohms plus 4 volts minus V out over 10 kiloohms is equal to 0. So the equation is much messier, but it's still a one equation, one unknown system for our calculator to solve. Which brings us to our third step. Solve our KCL equation for V out, which in this case, I'm actually going to have to use a calculator, so give me just a moment. So 4 over 6,000 minus 0.002 plus 4 minus 7 over 5,000 plus 4 minus x over 10,000 is equal to 0. Solve. I got V out to be negative 46 over 3 volts. So this is literally the hardest possible thing I could ask you guys to do. And to be clear, this circuit has no practical use either. It's just hard for the sake of being hard. And it can still be solved with the simple 3-step process that we developed in this class. All right, so does anybody have any questions? So what we are going to be doing on Wednesday's class is looking at how we use op amps for specific things, okay? So today's lecture was really all about how they behave and how to do the circuit analysis. We didn't talk about what their application is at all. The operational amplifier is, as the name suggests, an amplifier, meaning that it makes signals larger, and it's used to perform mathematical operations on analog signals. So on Wednesday, we're going to look at configurations of this amplifier, the inverting amplifier, the non-inverting amplifier, buffer amplifiers, summing amplifiers, differencing amplifiers, integrating amplifiers, differentiating amplifiers, all that kind of good stuff, to see how the op amp can be used to effectively perform mathematical operations on voltages and currents. Okay. That's its real purpose for analog signal processing. So for the majority of you guys, really all you have to understand is how to apply op amp rule number 1, op amp rule number 2, and then write a nodal analysis expression to solve for the output voltage. All right, so I'm just going to hang out on Zoom for a bit while you guys work on the in-class assignment, all that kind of good stuff. If you have any questions, feel free to put something in chat or just, talk to me directly.
Dr. Hartman.
Yes.
Quick question when doing transient analysis. So like for problem 4 on the homework, it's asking for different time variables, right? For like I1 at negative 0.8 seconds. For example, for me, when you do that, it's 4 is 0. So you have to find that equation.
So what homework set are you asking about specifically?
I think it's the one due tonight. I think 14.
And which problem?
4.
4.
Oh, this is mostly just in general. So when it asks for I1 at negative 0.4 seconds, it wants it obviously the equation before the switch happens.
So at negative 0.4 seconds, that's at DC steady state. So that's effectively just solving it at 0 minus, because everything is going to be the same before the switch changes state. So that particular value of time is completely irrelevant. Everything before 0 minus is the same thing.
Okay, that makes sense, because when I was doing it, I kept trying to find the equation and it kept giving me the wrong answer.
No, yeah, there isn't. It's going to be a value. So let's see, based on this. Oh, I don't want to try to do that in my head. Yeah, for finding I1 at 0 minus, I personally would do a source transform. Actually, yeah, the switch is closed but opening. Yeah, so a source transformation, and then current division, and that'll give me just some number. One thing for this particular problem that I do want to point out, though, is that you aren't asked specifically to find the inductor current. That being said, you need to know what the inductor current is so that you know how to analyze the circuit at t is equal to 0 plus.
Yeah. But when you go into DC steady state, wouldn't that 48 ohm resistor cancel out as well?
Yeah, so the 48 ohm resistor is going to be shorted. So I'm saying if you do a source transformation, you're going to have 64 over 4. What is that? 16. So 16 amps in parallel with 4 ohms, in parallel with 40 ohms, in parallel with 8 ohms, and then you just figure out how much flows through the 8 ohm resistor. And in truth, the inductor current at t is equal to 0 minus will be the same as I1 anyway. since all of I1 will flow through the short that is the 8 Henry inductor and avoid the 48 ohm resistor. Cynthia, do the ICA 16. We'll just we'll throw 15 away. Any other questions about the homework or anything? What about homework 15? I would still do it like there isn't, okay, I will put up a submission portal for 16 here shortly. And just as a heads up, there isn't a number 17 because the lab that we're going to do on Wednesday usually takes so long that we don't have time to get to an in-class assignment. So with regards to doing homework 15, I'm on the fence here because like you're gonna get extra time to do homework number 16 because it's not going to be due until later on in the week. Homework 15, as I mentioned the other day, is largely more practice on nodal and mesh than it is transient analysis. That being said, if you can do those problems, you can easily do anything I'm going to put on the exam. So I would argue that it's good practice there. So I don't really want to just throw it out. And then for homework 16, also, since we effectively did it in class today, you've got plenty of time to work on homework 15 because you don't have to worry about the op amp homework thus far.